College Marampally, e-learning.
Welcome back to the lecture series on computer networks. I am Jasir MP, Assistant Professor, Department of Computer Applications, MES College Marampally. In this lecture, we are going to have a look at analog and digital signals. As you all know, to be transmitted, data must be transformed to electromagnetic signals. The data could be analog or digital. The term analog refers to information that is continuous and digital refers to information that has discrete states. The human voice or natural sound is a classical example of analog data, which is continuous and non-periodic and can take any values in a frequency range. On the other hand, modern computers represent data as binary bits 0 or 1 is a classic example of digital data. Now, the topics discussed in this section are analog and digital data, analog and digital signals, periodic and non-periodic signals. As you know, analog signals can have infinite number of values in a range. Digital signals can have only a limited number of values. The figure shows a non-periodic analog signal on the left-hand side and a non-periodic digital signal on the right-hand side. The differences between them are self-explanatory. You can easily recognize that the analog signal assumes a continuous range of values, whereas the digital signal is clearly having a limited set of signal levels. In data communications, we commonly use periodic analog signals and non-periodic digital signals. Now, the periodic analog signals can be classified as simple or composite. A simple periodic analog signal is nothing but a sine wave that cannot be decomposed into simpler signals. A composite periodic analog signal is composed of multiple sine waves. We discuss sine wave, wavelength, time and frequency domain, composite signals and bandwidth in this section. As you can see, a sine wave is a mathematical curve representing periodic oscillations of constant amplitude as given by a sine function. The figure shows a sine wave in the time domain. Now, consider two signals with same phase and frequency, which means the rate of change and the starting point are same for both the waves, but the amplitude is different. As you could clearly see in the picture, figure A is showing a wave with a peak amplitude which is higher than the peak amplitude of figure B. Now, amplitude is nothing but the distance between the resting position and the maximum displacement of the wave. Frequency is the rate of change with respect to time. Change in a short span of time means high frequency, and change over a long span of time means low frequency. If a signal does not change at all, its frequency is zero. If a signal changes instantaneously, its frequency is infinite. Therefore, frequency and period are the inverse of each other. F is equal to 1 by T and T is equal to 1 by F. Now, two signals with same amplitude and phase can have different frequencies. Figure A shows a sine wave with a frequency of 12 Hz. So, automatically, the period is 1 by 12 seconds. On the other hand, figure B shows a sine wave of frequency 6 Hz and period as 1 by 6 seconds. Simply, we can say that frequency is the number of waves passing by a specific point per second. Period is the time it takes for one wave cycle to complete. Table shows the units of period and frequency. Period is measured in different units of time, seconds, milliseconds, microseconds, etc. And frequency is measured in hertz. Now, phase describes the position of the waveform relative to time 0. As you could see, figure A shows a wave with a phase shift of 0 degrees. Figure B shows a sine wave with a phase shift of 90 degrees. C shows a sine wave with a phase shift of 180 degrees. Phase is nothing but a particular point in time on the cycle of a waveform measured as an angle in degrees. Now, the wavelength and period. Wavelength is the distance between identical adjacent parts of a wave. You can see in the transmission medium, the wave has reached a particular point at time t, and after a period, capital T, the wave has advanced by a complete cycle, that is wavelength, in the direction of propagation. The time and frequency domain plots are two possible representations of a sine wave. In time domain, a sine wave is represented totally with all the possible values that it is holding, and in frequency domain, the sine wave is represented with just a single spike against the corresponding frequency and amplitude values. This comes handy when composite signals are represented. A complete sine wave in the time domain can be represented by one single spike in the frequency domain. The figure shows time and frequency domain of three sine waves with frequencies 0, 8 and 16. Figure A shows the time domain representation, which is a bit messy with multiple waves, and figure B shows the frequency domain where these three waves behaviors are represented with three single spikes. A single frequency sine wave is not useful in data communications. We need to send a composite signal, a signal made of many simple sine waves. If the composite signal is periodic, the decomposition gives a series of signals with discrete frequencies. If the composite signal is non-periodic, the decomposition gives a combination of sine waves with continuous frequencies. The figure shows a composite periodic signals of three frequency levels, which is not so common in data communications, this sort of signals. Let's assume that it's a three frequency alarm system. And this composite periodic signal could be decomposed into three harmonics such as frequency F, frequency 3F, and frequency 9F, which is represented in the time domain as shown in figure A, or it could be represented in the frequency domain as shown in figure B. This figure shows a non-periodic analog signal which could possibly be extracted from a telephone communication. Figure A shows the signal in time domain, and figure B shows all the possible ranges of that non-periodic analog signal from 0 to 4 kHz. The bandwidth of a composite signal is the difference between the highest and lowest frequencies contained in that signal. So, for a periodic signals, the bandwidth will be the difference between the highest component and the bandwidth with the lowest component. The same is true for non-periodic signals as well, but there will be no break in the frequency spectrum. The only difference is the component frequencies will be continuous, not discrete as shown in figure B. Imagine a periodic signal is decomposed into 5 sine waves with frequencies of 100, 300, 500, 700 and 900 Hz. What is its bandwidth? And draw the spectrum assuming all components have a maximum amplitude of 10 volt. We know that the bandwidth will be frequency highest minus frequency lowest, which is 900 minus 100 is equal to 800. The bandwidth will look like 5 spikes in the frequency domain. All the amplitudes corresponds to 10 volt, and each individual spikes corresponds to the respective frequencies. Today we discuss analog signals, simple sine waves and composite sine waves, periodic and non-periodic analog signals, properties of waves, and time and frequency domain representation of analog signals. In the next class, we'll be discussing digital signals. Thank you.